So we're on to a new lecture topic in this chapter, and this lecture topic is going to focus more on the pHs of these compounds, or not really of these compounds, but the solutions that these compounds are in, because we said that the pH is really the environment that these compounds are in, and the pKa's represent the compound in particular, not of the solution or the solvent. So we need to go back and really define pH. We know what pH really means. pH is basically the hydrogen concentration in molarity of the solution that we are working with. And this pH is really defined as the negative log of that hydrogen concentration. So if we know what that concentration is in molarity, we basically plug it into this equation, we log it, we take the negative of it, and we get the pH of it. If we have the pH and we have to solve for the hydrogen content, we do that by first getting rid of the negative and moving it over. So for instance, if this was 3.01, this would turn into a negative 3.01, and then we inverse log it. So we do 10 to the negative 3.01, and this will give us the hydrogen concentration in molarity if we're ever asked to solve those types of problems. So we've also talked about the difference between pH and pKa. Again, pH is of the solution that compound is in, and the pKa is of the actual molecule itself. So these are referencing two different things. They're not the same. That is a misconception that people have, but they are related. Okay, they're related, but they're not identical. So pKa will be the deciding point. This is something that we've talked about already up to this point. pKa and pH are related, and pH will affect the pKa or vice versa, depending on how you want to look at it, and the structure of a molecule. So again, the best way that we can kind of dive into this is just looking at an example. So here it says, write the form of a compound that predominates in a solution with a pH of 5.5. And they give me A, and A gives me ethanol, CH3CH2OH, and it says pKa is 15.9. Okay, so that means that this is an acid, and the hydrogen that's probably going to get donated is this one right here. But it only can get donated under a certain condition, and that condition is the pKa condition. This pKa is 15.9. So therefore, the only time that this molecule will spit that hydrogen off is if my pH is greater than 15.9. Well, here in this example, my pH is 5.5. So it's way, way lower than that pKa right now. So if we dump alcohol into a solution that has a pH of 5.5, guess what? Nothing happens. This is going to stay as ethanol, and it's going to stay as CH3CH2OH. That's just the way that it's going to be. All of that is determinant on the pKa value of that compound. For part B, this is a protonated alcohol. And this protonated alcohol, we know, plummeted in pKa value. We saw that in our table very early on. And it gives me the pKa value here, in case we didn't remember it. The particular pKa value for protonated ethanol is negative 2.5. All right, well, pH of 5.5 is above negative 2.5. All right, my pH is greater than the pKa. So for that reason, this ethanol will decide to spit off one of these hydrogens, and it will go away. It will donate that to solution because this pH is requiring it. The pH is 5.5. The pKa is negative 2.5. This molecule is going to say, I'm keeping it. I'm keeping these hydrogens until you go above negative 2.5. When you get greater than negative 2.5, then I'll spit this off. But until you go higher than negative 2.5, you ain't getting it. And this solution is higher than negative 2.5. You would rather have $5.50 in your bank account than being in the hole $2.50, wouldn't you? So this pH has a greater pH value. Same reasoning for part A. This molecule says, I'm keeping it. You're not getting it from me. And the only time that you're going to get that from me is if you go above a 15.9. And until you go above a 15.9, I'm going to stay a hold of this hydrogen, and I'm not going to donate it because I'm greedy. I don't want to share any of my hydrogens. They're mine. They're not yours. And that's just the way alcohol thinks. All right. Well, C is a protonated amine. This is a positive NH3. We know that amines have pKa's of around 40, but protonated amines really plummet that pKa value down, and that pKa value is an 11. Okay, so we need to draw the form of the compound that predominates here. And the form of that compound, well, this molecule says, I'm keeping it. I'm keeping it until you get above an 11. Sorry, this is mine. This is my hydrogen. I worked for it. I earned it. And you're not taking it away from me. So because of that, it's going to force the solution to rip it. And the only way that that solution can rip that hydrogen from that molecule is to go above an 11. Well, this pH is 5.5. So it is way, way away from 11. So this molecule says, showed you, didn't I? I told you weren't getting it, and you're not getting it. So this molecule stays the way that it is. It's CH3NH3. So again, these are the types of questions that you might see in the assessments online. It's also the types of questions that you'll see in the tests that I'll give out too that correspond to this lecture material. Here's another example. For each of the following compounds, write the form that predominates in a solution with a pH of 5.5. So again, it's the same types of questions, but it's just more chances of me to practice what I have learned so that I'll feel a little bit more comfortable with it, and that's what we're going to do. So for part A, here's my molecule, and the molecule says I'm keeping it until you go above a 4.76. Well, this pH is above a 4.76. So that means that this molecule will behave as an acid, and that solution will rip the hydrogen away. So this is the form that predominates at 5.5. For part B, this molecule says I'm keeping it until you go above 11. Well, it's not above 11. So this molecule stays intact. It does not act as an acid yet. It could, but as of right now, it's not acting as an acid. It's going to stay and keep that hydrogen. For C, this is protonated water, which is just really the definition of an acid. This pKa is a negative 1.7. The molecule says, I'm keeping it until you go above a 1.7, negative 1.7. Well, it is. It's a 5.5. So this H3O plus actually turns into H2O. It does lose the hydrogen, and when it loses that hydrogen, we have H2O that's neutral at this point. D, HBr. This is one of those strong acids, remember? That pKa is negative 9. Well, 5.5 is way above negative 9. So this molecule does not keep the hydrogen. It didn't want it in the first place. We said it was a strong acid. It's going to get rid of it when it can, and it loses that hydrogen, and we have a negative bromine that's left over. The question I always get, does it matter how I draw the bromine, put the negative in front or the negative behind? I don't really have a personal preference. Some people do. I don't. It means the same thing to me, doesn't it? I mean, if you think that the one to the left and the one to the right is different, well, I hate that you live that type of life, but to me, they are identical. I don't really care which side you put the negative on. That makes no difference. You've given me the right answer, and I'm going to give you the credit for it. For E, a protonated amine, or really an ammonium here. That's what we would call that, a positive NH4. pKa is 9.4. The molecule says I'm keeping it until you go above 9.4. Well, this is not. It's 5.5. So this is the structure that it's going to have at a pH of 5.5. For F, we have HC triple bond N, pKa 9.1. The molecule says I'm keeping it until you go above a 9.1. Well, this is not. It's 5.5. So this acid stays intact, and it keeps the hydrogen, and it doesn't spit it off until we increase the pH of that solution. HNO2, pKa of 3.4. I'm keeping it unless you go above a 3.4. Well, it is. So it loses the hydrogen, and we have an NO2, and there's a removal of a positive charge, so that is a negative. HNO3. I'm keeping it until you go above a negative 1.3. Nitric acid was one of those strong acids that we talked about. So this is not uncommon. We know it's going to spit off the hydrogens whenever it can. So it will. And we have an NO3. It's removed a proton, removed a positive charge, so therefore it's negative. And then finally we have this I piece. The I is an OH and then an NH3. And here they don't give me really a pKa for that, do they? So what they want me to do here is that they want me to kind of use common sense, and they want me to look at this, and they're kind of being tricky with me because we've talked about OH groups. These are alcohols, right? And that alcohol group, that OH group right there, normally had pKa's of around 15. They want me to remember that. And then here we have a protonated amine. Well, we knew that amines really have really high pKa's. We've talked about those high pKa's. We said that those high pKa's were around a 40. Well, protonated amines lowered it. It really plummeted those pKa values. But is it to the point where 5.5 is going to play a role? Well, here, protonated amines, if you didn't remember, have pKa's of around a 10. So my alcohol has a pKa of a 15. My protonated amine, that has a pKa, but that pKa is a 10. So this hydrogen, I'm keeping it unless you force me to go over a 15, and you haven't. And then this one, this hydrogen, I'm keeping it until you force me to go over a 10. And we're not anywhere near that again. So this is the structure that that molecule will keep because we are not over either pKa in that value. So the reason that I like this one is because it lets you know that 2 pKa's are okay. It's fine if you have more than one, no big deal. You treat them differently. You treat them separately. You don't have to add these numbers together. You don't have to take an average of these numbers. You don't have to do anything. Look at all of the pKa values, and if this particular pKa value that's associated with that hydrogen, if this is affected, then that hydrogen will also be affected. But if all the other pKa's are not, all those other hydrogens, they are not affected at all, and they stay on the molecule. It's just like looking at two different example problems. That's the only difference. You're looking at 2 pKa's on one molecule instead of only one. But the rules don't change, folks. The rules should not change, should they? Because we are learning a procedure. And if it's true, that procedure needs to be applied to everything that we look at. And there's no exception here. So don't let those questions throw you off. If you get 2 pKa values, okay, no big deal. Just treat them as separate problems. And if it is over, then we'll remove the hydrogen. Whatever. Don't let these questions throw you for a loop. So that's where this question or this video is going to stop. In the next video, we are now going to truck on and we're going to address buffers a little bit. Okay, we've talked about pH, how pH affects pKa value and vice versa. Now we need to talk about buffers because this does play a role in organic. We probably won't see buffers after this, though, honestly. So we are not going to go full-blown buffer lecture. We're going to introduce a buffer. We'll talk about a buffer. We'll talk about how to make a buffer. But that's it. That's as far as we're going to go. We're not going to do any example problems, any type of calculations, or nothing that's associated with buffers. That's general chemistry class stuff, right? That's not organic. But we at least want to mention it because it does relate to acid-base chemistry. So in the next video, we'll talk about buffers, and we might finish the lecture module up.